In this video, we're going to take a look at topic 7 of our C1 work, which is acids, bases and salts. Acids, bases and salts. So acids are things that you're very familiar with, and you'll see on the top of page 3 there's a list of some of the common acids, and in the lab quite a few times we've used things like sulfuric and hydrochloric acid. Nitric acid, another one we use occasionally. There are other acids as well. Phosphoric acid we occasionally come across. This one you're probably very familiar with, ethanoic acid, or the historic name for that was acetic acid, and that's basically the acid that's in vinegar. So whenever you put vinegar onto your chips, that's really what gives you the taste of the acid and so on. And citric acid you're familiar with from citrus fruits like lemons, oranges and so on. Now, most acids have got properties that are very similar to each other, and that's why they're classed together as acids. So for example, although you shouldn't taste these in the lab, you know from your experience of eating things like lemons that they are quite sour, and similarly vinegar is sour, and that's the taste of acids. They all taste sour. The other thing about them as well is that we can test for them, and there are 3 tests that are commonly used for acids, alkalis and neutral substances, things that are neither acids nor alkali. And the first is litmus. Now, let's just remind you of the use of litmus. So there's a little short video here just to show you how litmus is tested and things. So you'll see a range of substances here, from hydrochloric acid, sulfuric acid, ethanoic acid. We've got some water. Usually the water that we use in the lab is deionized water. That's water that has had all the chlorine and things removed from it. Ammonia and sodium hydroxide. So we're going to use the litmus to test the sodium hydroxide, which is here, the deionized water and the hydrochloric acid. So let's see what happens with it. Now with litmus there's 2 colours of paper. This is blue litmus, and the first thing we'll do is dip that into an alkali, and you can see that the blue litmus stays blue. We'll come back to that in a second, because we're going to use another type of litmus in a moment. In acid, on the other hand, the litmus turns red. And then we'll dip the blue litmus into deionized water, and it stays blue. Okay, so usually you use 2 types of paper. So the other is red litmus. Now if you put that into alkali, the red turns blue. And if you dip the red litmus into hydrochloric acid, it stays red. If you dip the red litmus into water, it stays red. So if you look at what's happened there, with all of those, what we found is whenever we had our acid, let's get our presentation back up again. So when we had our acid, the litmus turned red. Alright, so litmus turns red. So whether it's blue litmus or red litmus, it stayed red. So usually what we do, if we think something's an acid, we take that red litmus, if we think something's an acid, we take the blue litmus, and the blue litmus turns red. So we want something that will turn to that colour. So blue litmus turns red. On the other hand, alkalis we saw there, it did the opposite. The blue litmus didn't change with it. So if we want to test for alkalis, we normally take red litmus, and red litmus turns blue. And then we saw with the water, both the red litmus and the blue litmus went into it, and nothing happened with it, so it doesn't affect it. So acids will turn blue litmus red, so they turn litmus red, and we normally use the blue litmus for it. Alkalis turn litmus blue, so we normally use the red litmus for it, and neutral substances aren't affected by it. Now, all that litmus does is it tells us acid, alkali and possibly neutral. It doesn't tell us anything about that. So if you go back to, for example, our list of acids, things like sulfuric and nitric acid are very strong acids, but we can put vinegar onto food, and litmus doesn't tell us any difference between those. So litmus simply tells us if a substance is an acid or an alkali. Alkalis we're a bit less familiar with. Now the one that we will use most commonly in the lab is that one, sodium hydroxide. It is used in the home. For example, if you get Mr. Muscle oven cleaner, it's a solution of sodium hydroxide. Other examples of alkalis would be things like ammonia solution, and that's quite often used as a cleaner. So if you have any Brasso at home or certain floor cleaners, they'll contain ammonia. Lime water is also an alkali, and that's what we use to test for carbon dioxide. And baking soda, if you dissolve it in water, a solution of that is slightly alkaline as well. So there's our common alkalis. Now the one to try and remember is sodium hydroxide, and we'll see it a wee bit as we go through. Neutral substances, fairly obviously the most obvious neutral substance, water, as we saw there. Ethanol is also considered to be neutral. It's got a pH of 7, which we'll come to now. So, acids, alkalis, and so on, quite often we have risks associated with them. So to communicate those, we often use these hazard symbols. So be familiar with those. That's the symbol, remember, for corrosive. So if you spill it onto your skin, that would actually harm living tissue, and that's the idea of the picture there. But dilute acids can quite often just be slightly irritating. So these are what are called a moderate hazard. Remember, this symbol is for a moderate hazard. In other words, if you got them onto your skin, it mightn't necessarily cause burns, but it might cause some irritation like itchiness and things like that. So these are the two labels that we use most commonly. So with sulfuric acid, we'll quite often see things like this on it. With hydrochloric acid, particularly dilute solutions, hydrochloric acid, these. Now, in both cases, we have to do a risk assessment. So concentrated acids that have this corrosive symbol, they can cause damage to things like living tissues, particularly eyes and skin, and even sometimes the vapors with some of those can be harmful. To avoid the risk, the most obvious thing, safety glasses. And the reason we mention this is quite often they will say this in a question from something like SEA, where they'll ask you why, what would be a safety precaution. And safety glasses are the most obvious ones. The other thing is that we do in the lab is we usually use a dilute acid, so the lowest possible concentration. And if necessary, particularly with the concentrated acids, if you want to protect your skin, you could wear gloves. So have we read over those and think about particularly the safety glasses and the gloves as being a way of trying to mitigate against those risks. If you do have an accident, for example, if you spill acid onto the skin, you've got to wash it off. So you flood the area with lots of cold water, usually for at least 5 minutes. If you've got a concentrated acid, and up to about 10 minutes. And if clothing's contaminated, you try and remove it if possible, and if not, just flood it with lots and lots of water. So if that's if an accident does occur. With dilute acids, again, there's the risk of it. If you get them onto the skin, they can cause irritation. But even the dilute acids can cause damage to the eyes. So you must wear those with dilute, with the hazard symbol like this, where we've got the moderate hazard symbol. You always must wear safety glasses. So that's the number one thing with wearing these. If you're working with these, you have to obviously work with care. For example, set at the center of the desk so that you don't knock it off and spill it. And again, even if you spill a little bit of this onto your skin, you flooded the area with lots of cold water. Okay, so a little improvement in terms of testing for acids and so on is if we want to try and see if acids are strong acids, those ones that would cause, for example, damage to skin, or weak acids, things that we can put into food. And what we normally use is universal indicator solution. And universal indicator solution, or as I'll show you in a video shortly, you can also get as a paper, basically gives us a pH number. And you remember we were doing this back in junior form. So the pH scale, if we want to use the universal indicator solution, what we do is we place the solution under test into a test tube, add a few drops of universal indicator and shake and mix it thoroughly. And then you look at the colour developed and you get different colours. And depending on the colour, you match it to the scale. So for example, if things are neutral, they tend to be green in colour with universal indicator. If we go this way, lower pHs, these are the acids. And the more down this scale you go, the stronger the acid. So for example, 0, 1 or 2 is considered to be a strong acid. We'll come back to that in a second. And they're at the red end of the colour scheme there. If you've got a weak acid, it tends to be orange or even up to about yellow. And then if you go to the other side, alkalis, strong alkalis, pH 12 to 14, they tend to be a purpley colour. And then in this region here, it tends to be more of a blue. I'll show you another pH scale shortly that maybe shows that a little bit better. Okay, so any solution with pH less than 7 is acidic. pH with greater than 7 are alkaline, and pH 7 are neutral. So I always think, if you remember, 7 neutral, and then the further away you go from that, the stronger it becomes. And particularly when you get up to this end, 0, 1 or 2 strong acids, 12, 13, 14 strong alkalis, and then in between those are the weak acids and alkalis. So let's show you that in practice. So let's start off with a universal indicator solution. And if you want to test with universal indicator solution, you'll see that you normally put about a centimetre cubed of the substance under test into a test tube. So that's basically one of those droppers filled up to the stem there. And then we add a few drops of universal indicator, just enough to give a nice colour, so that the colour develops. So you'll see a few drops of universal indicator being added there. And then you shake it up. And you'll see in the foreground, just about in this corner here, you'll see a little bit of the pH scale that you use to test for that. Okay, so you're quite familiar with that from junior form, and that's something that you use to test for it. Now, you don't have to just use universal indicator solution. You can also buy a paper that'll do this. And here's the paper. So if we dip that into the sodium hydroxide, and that shows up quite nicely, that sort of dark color there. So you're getting up towards the purpley blue end. With water, hard to see just with the video there, but if you look at the drop there, you can just about see a green color with it. And then the acid, and that's a very definite red. And you'll see this time the paper had 3 colors in comparison to the litmus that only had the 2 colors. Universal indicator is basically a mixture of indicators, and that gives us the several colors from that point. Okay, so universal indicator at the top there, if you want to highlight up, it's a mixture of different indicators. And then it's got the advantage, it not just shows us if a substance is acid or alkali, it also shows us the strength of the acid. It gives us a pH number. Now, the sort of colours there, so there's a picture of the scale of colours. So green, that one there, is neutral, and that's basically what we see with water, deionized water, so water that's had all of its chlorine and things removed, and that's a very different green, and you'll see that that matches to pH 7 there. The blues and sort of darker, even into purples there, and if you look at this one, this is almost like a dark blue there, so it's gone from light blue to a dark blue. So that substance would be a strong alkali, up around about pH 12. This one's a lighter colour, and you get even a bit lighter again, so that's probably about pH 10. So that would be a weak alkali. This is going to be a strong alkali. And then come down this end. So these 2 test tubes here are hydrochloric acid and sulfuric acid. And you'll see there, with that particular scale, 1 or 2, there's certainly definitely the red end of things there. So that would be the strong acids. And then there's vinegar, ethanoic acid, which is a weak acid. And so universal indicator can give us that range of colours. So this table is the thing that SEO have put in terms of the numbers that they use. So anytime they communicate numbers of pH, this is what they base it on. So try and get familiar with this and know this one, and know the number range, and then where we've got weak and strong. So 0 to 14, so if you list that down, go to the middle, 7, green, is neutral. Go down to the left-hand end, they are getting acidic, anything less than that is going to be acidic, anything less than 7 is acidic. So 0, 1 or 2, red colour, that's the strong acids. 3, 4, 5 and 6, orange and yellow, they're the weak acids. Up to the far end here, so anything above 7 is alkali, so 12, 13, 14, purpley colour, strong alkali. And then 8 through to 11, greeny blue, right through to blue colour, those are weak alkalis. Examples, the strong acids, so if they ask you for those, the common laboratory ones, hydrochloric acid, sulfuric acid, nitric acid. The weak acids, ethanoic acid. Carbonic acid is also a weak acid. That would be where you dissolve carbon dioxide in water. I'll come back to that one. And we haven't listed it there as well, but citric acid would fit in there too. The weak alkali, the common one that we use, ammonia. And then the strong alkalis, sodium hydroxide and potassium hydroxide. So know that little pH scale and how to use it. Okay, so advantages of using universal indicator. You can see it obviously gives us a range of pH colours. You can see it's quite quick to use. So if you get the paper, it's only a matter of dipping it in and then using it. Now, it doesn't need any calibration. Now, I'll explain that in a moment compared to what we call our little pH checker or pH meter, which will show you. And so therefore it is able to be used straight away. Disadvantages is it needs a judgment of colour. So quite often you're looking at it and going, is it that dark blue or is it a lighter blue than that? So you can have a difference of a pH number there. And so it's quite often difficult to determine between two pH numbers. And that could make the difference between classifying a substance as a strong acid and a weak acid. And also, full range indicator only gives the pH to the nearest whole number. You can get slightly more accurate ones, and they take a little bit more getting used to, but most universal indicator you come across only gives pH to a whole number, and you'll see why that's a slight disadvantage in a moment. Now, sometimes if we want to try and get pHs, and sometimes get pHs maybe a little bit more accurately, and by accuracy we mean closer to the actual value of it, we can use things like pH meters. And this picture shows a range of pH meters, and if you look at things like this one here, this would be quite an expensive one to buy, probably several £100 for this one. We tend to use a little pH meter like this in school, which we buy for about £40 or £50, and can be used to test for pH. And there's various other ones you can get pH meters up to many hundreds, if not thousands of pounds, depending on the accuracy that you want with it. Now, to use these pH meters, you might think, well, this is great, you can just dip it in and get the number, and you do, and you've no judgment with this, so you see there's an advantage, you just look at the scale and read off what's on the scale. You can see there that's given it to 2 decimal places. Quite often when you buy these, they will guarantee it maybe to say 0.1 of a unit, so quite often it's accurate at 0.1, which again, is, you can see, is much better than some of that full range universal indicator, where it's only accurate to 1 unit. So this will give you a greater accuracy, and as I say, quite often the manufacturer will stand over about 1 decimal place, so to the nearest 0.1. And you can see this one here, for example, is even more. It's got 3 decimal places there, so that might be given to an accuracy of 0.01 or 0.001, depending on how good the instrument is. So why do we use it like this? Well, to use it like this, you might think this is great. All you have to do is switch it on, your battery operated, and then dip it in. The slight disadvantage is they need a thing called calibration. So I'll show you this just very briefly with this. And this is from Hannah, the group that I make these. And you'll see what calibration is with this. And calibration is basically where you keep the meter showing a particular figure. And you'll see to do this, what you've got here are 2 solutions. These are in these little bags. And then you put it into one of the buffer solutions. This was called a buffer solution. Put it into the buffer solution. And then you'll see there's a button to push. And then it'll read to that one. Then you put into the second one. And read to that one. And then stores it. And then that allows you to test it. Now, that seems as if there's not very much to it, but it takes time. So for example, if you were doing a class set of those, you'd have to do that maybe for say 12 or 13 meters. And so calibration can actually be a little bit of a disadvantage. It takes a bit of time to set that up. So quite often our lab technician, if we're doing that as a class experiment, takes time and sets up and calibrates the meters beforehand. And that's one of the slight disadvantages to them. So the pH meter can be used to measure pH. It's quite often more accurate than the universal indicator, so quite often accurate to, and you can see ours there, about 0.2 pH units. That's the accuracy of the little meters we use there in school. The advantage is there's no judgment of colour this time. You simply put it in and then you read it off. It can give accuracy, right, so much more to 1 or 2 decimal places. You saw some of those there. And it can also be used, for example, if you're during a reaction, if you're trying to follow the pH as a reaction takes place, you can put that in and just watch the meter and even record down the different values as it goes on. So there's lots of advantages to using the pH meter. The disadvantage, as we said, is that it needs that calibration. Right, so you need to prepare it by dipping into 2 solutions of known pH before you use it. So therefore, if you're just doing a one-off reading, it can be relatively slow, and that would be the disadvantage of it. Okay, the experiment that we do sometimes to compare this, so if in the lab we usually give you different solutions and we put universal indicator, use the universal indicator, get the pH, and then you compare it with the pH meter. And I'll give you typical values. You can put these into your table in your notes. So sulfuric acid typically turns out at 1 when you use something like the pH meter, and we get you to read it to the nearest sort of 0.1, and it tends to be about 0.9. So you can see it's in the same region, but of the two, obviously the pH meter is more accurate because it's given at 1 decimal place. Sodium hydroxide, typically pH 13. Again, using the pH meter, turned out something like 12.9. Water should be 7, and with the pH meter, if you've got pure deionized water, it should be 7.0. Ammonia would tend to be about 9, and again, you get something similar with a pH meter, but slightly more accurate. And ethanoic acid, pH 3, it's a weak acid, and with a pH meter, something like 3.1. Now, you can see there the more reliable one. Well, you'd have to dip it in a couple of times. They're probably both equally reliable. They'll give the same result. Slightly more accurate, maybe, is the pH meter because it gives it to 1 decimal place. So they're reliable, and reliability is basically if you keep doing it over and over again to get the same result, and you should do. Hopefully they're both reliable. But of the two of them, the pH meter is slightly more accurate. Okay, so that finishes our introduction on this, and you could try the key questions on page 7 to do this.